Okay, so the second part of the objective is being able to write a power function from a collection of points. So power function has the form y equals a times x to the b. Notice the relationship between this and the exponential is that the variable and the base thingy have been switched. So the variable is the base this time, and the exponent stays constant, our b value. So just like before, we only have two parameters. We have the a and the b. We only have two parameters, which means that we only need 2 points and 2 equations in order to solve it. And we're going to solve it by substitution once again. Okay, now it seems like this one might be easier, but it's not. It's a little bit trickier, as you'll see right here in exercise 7. But don't let that scare you away. Oops, that's not the right button. This one is. So we're going to write this as y is equal to a times x raised to the b. And let's plug in our points for x and for y. So in the first one, 6 is equal to a times 4 raised to the b power. And then the second one, 15, is equal to a times 8 raised to the b power. Just like we did before. I mean, you solve it similarly as far as the substitution part goes. You're going to solve that first one for a. So a is equal to 6 divided by 4 raised to the b. Put that expression in for a. Second equation. So 15 is equal to 6 divided by 4 raised to the b times 8 raised to the b. Now we're going to keep simplifying the right side of that equation. 6 times 8 to the b over 4 to the b. Now I'm going to do something a little unconventional here. I'm going to separate the things that have the exponent b's with them. So this is going to be 6 times 8 to the b over 4 to the b. Whoops, 4 to the b. Okay, so think of the power property of exponents. Whenever you have a power raised to the power, you multiply the exponents. So working that thing backwards, what this really is 6 times 8, there we go, divided by 4, all raised to the b power. So notice I would, if I was going to apply the power property of exponents, I would multiply each of the things that are inside the parentheses here by the exponent b. Multiply their given exponents. So all of this is equaling 15. So divide by the 6. When I divide by 6, 15 over 6 divided by 3 is 5 halves, is equal to, and then that's just 2 raised to the b power. And in order to solve an exponential equation, you need to take the log of both sides. We could take log base 2, or just take your favorite log so it changes the base for you. Okay, so I'm going to come up here. So I have the natural log of 5 halves is equal to the natural log of 2 raised to the b. The b gets to come out front. Natural log of 5 halves equals b times the natural log of 2. And then divide by the natural log of 2, we can get our base. B is equal to the natural log of 5 halves divided by the natural log of 2. And notice that would have been how we would have changed the base if we would have taken the natural log of 2. So calculator time. And clear this out. Natural log of 5 divided by 2, close those parentheses, divided by natural log 2. Close them again. And I get about 1.3. I'll give it about 1.3. Okay. So our b value, our exponent, is about 1.3. Now, plug it back into the original equation so we can find our a value. So a is equal to 6 divided by 4 raised to the 1.3 power. But we're going to use the number that's in the calculator to get that. So pull that back up again. 6 divided by 4 exponent, and then just second answer to pull that back in, and I get 0.96. 0.96. No, that was not approximately equal to. It was equal to 0.96. So our equation is y is equal to 0.96, and this one is the base is the exponent, and the number we got for b is the actual exponent. I'm not sure I said that right. I'll find out in editing. So there's our equation. So here are the steps involved in solving yourself a power equation, writing a power equation from a collection of points. It's very similar to what we did for the exponential one. Substitute your points in for x and for y into y equals a times x raised to the b power. Solve this simpler equation for a and substitute that expression into the other equation in the place of a, so it gets rid of it. Solve the new equation for b, and that's going to involve a logarithm because we're solving an exponential equation. Okay, once we get our b, stick it back into one of the original equations, find the a, and then finally write the answer. Now I think you're going to want to practice this, so why don't you right here? So exercise 8, find a power function that goes through those 2 points, and then come back and see me. So were you relieved when this one worked out to be something a lot simpler than the one we did together? Were you? Probably. So here's our answer. We get y equals 3 times x raised to the 4th. Again, whenever we set up our equations and do the whole thing by substitution, let's review this part right in here. Okay, coming from this part. Okay, so whenever I substitute my a value in together, take both of those numbers that have the common exponent and write them as a fraction and bring that exponent out, right? It's just using the power property of exponents. Okay, and then you can divide by the coefficient, and then you can take the log of both sides and get your, not your base, but your exponent, right? Solve an exponential equation. You get the solve an exponential equation by taking the logarithm. There you go. Okay, so if we solved that one correctly, we should have gotten y equals 3 times x to the 4th, which is what we got. Okay, so that's what that equation looks like. So really kind of flattened out parabola looking shape. All right, so let's do the same thing that we did before. Let's take x comma natural log of y. Let's graph that thing. If you want to do that in your graphing calculator, go ahead. Or just look right here. Well, that's interesting. I mean, it looks kind of cool and stuff, but it's not very helpful at all. All right, so let's try something different. Not x comma natural log of y. What about natural log x comma natural log y? Right? Do natural log of both of them. So when we do that, watch what happens. So this one you can't easily do on the calculator, so it's going to be right here for you. So here's the original equation again, graphed out, and then if I just take my points, like that point A, take the natural log of x value, take the natural log of y, here's its new point. Okay, pick another point that is on there, take the natural log of both of them and plot that as a new point. Let's take a third point on there, because any 2 points are going to make a line, right? So we need a third point at least so we can see what kind of thing it's going to be. So yeah, so take the natural log of x, natural log of y, and there's that third point. Hey, look at that. They do line up. They do make a line. More than that, though, if I were to take the slope of that thing, the slope of that is 4. 4. Look at the original equation. 4 is the exponent. That's cool, all right? 4 is the exponent. That's also the slope of that linear equation. So let me explain what's going on here. So in general, if you have a collection of points that you think fit a power model, a power function, then you need to graph both the natural log of x comma the natural log of y, and that one would have to fit a linear model in order for the original set of data to be a power model. Whew, right? Not only that, but the slope of that linear equation is going to be the exponent of the power model. All right. So again, let me go through an example so that you can see the math happen here, see what's going on. Start with y equals x to the 1/2. It's basically the square root function. It's a power function. It's a base raised to a power. Okay. Now let's take the natural log of both sides as we've done before. Okay. Over there on the right-hand side, using the power property, I can take the 1/2 and then just bring that out front. So here is our linear equation in terms of natural log x and the natural log of y. because the x didn't come out, the 1/2 came out, and the 1/2 is the slope, right? The number that's right out in front, that's the slope, and that gives us our power. So bear in mind again that what you're basically doing is you're graphing this on a log-log graph. The x-axis is not x-axis, it's a natural log x. The y-axis is the natural log of y, and then it takes that curvy graph and then straightens it out. If it straightens it out, then the original graph must have been a power function, and its slope was your exponent. Okay, so let's look at it in general then. Same kind of deal. Start with the equation, take the natural log of both sides. On the right-hand side, you have a log of a product, so break that up using the product property as the sum of the two logs. And then that b, that exponent, gets to come out front using the power property. And the b times the natural log of x, that's our slope, right? And the natural log of a, that's our y-intercept. So it's very, very similar to the exponential function. So let's look at this with kind of working backwards there. I had a set of data. I graphed it. I'm pretty sure it fits a power model. So then I graph natural log x, natural log of y, and here's the linear equation that I came up with. Natural log of y is equal to 3 times the natural log of x plus the natural log of 13. And we want to get the power model that goes with the original set of data. So, phone. Who's that guy? I don't know. Anyway, so here we go. Natural log of y is equal to 3 times the natural log of x plus the natural log of 13. Okay, let's take that exponent and bring it inside. So natural log of y equals the natural log of x cubed plus the natural log of 13. Over on the right hand side I have a sum of two logs, so I can condense that down as the product of what I'm taking the logs of. So natural log of y equals, and I'm just going to rearrange that to make that natural log of 13 x cubed. Right? You don't have a problem with that, right? They have the same logarithmic base, so what I'm taking the log of must be the same. So basically those cancel out. Y is equal to 13x to the third. So from the original equation here, this 3, that's the slope, that becomes the exponent. Very interesting. Okay, so in the next one we're going to do some more scatter plotting and some more regression.